All right, welcome again, everyone, and thank you for joining Trillium's webinar today on vertical pumps. We'll kick things off here by starting with a few introductions of today's presenters from Trillium's global engineering team. And I'll start with giving the floor to you, Luca.
Thank you, Dan. My name is Luca Carbonino. I have been working in Trillium, actually in Gabioneta, in the site in Nova Milanese, for 13 years, working as an R&D engineer, in particular hydraulic engineer, and I take care of what is the design of the new pumps from the scratch, let's say, so from the hydraulic point of view, but also from the mechanical point of view, and solving issues regarding new pumps, but also job pumps. I am a mechanical engineer. I hold a degree taken at Politecnico of Milan.
I'm Andrea Di Mella. I have been with Trillium for almost 12 years, working as a technical lead of vertical pumps and responsible for design, calculation, scheduling activities in La Spezia. I hold a master degree in mechanical engineering from Università di Pisa.
And my name is Dan Bolt. I have 16 years experience working in engineering with vertical pumps at Trillium at our site in Fresno, California. I am currently the Director of Engineering. I hold a Bachelor of Science degree in Mechanical Engineering from the University of California, Davis. And I'm also a licensed professional engineer in the state of California. So starting with a brief overview and background, Trillium Flow Technologies is a global company that provides a broad spectrum of pump and valve solutions to meet our customers' needs. We support our customers with a global sales organization and have multiple manufacturing plants and service centers around the world. On this slide, you can see a few of the various pump and valve brands and locations that make up Trillium Flow Technologies. A few of the pump brands that we'll be covering today while we discuss vertical pumps are Flowway pumps, Gabioneta pumps, and Turbomecanica pumps. So this slide shows some of the history behind Trillium Flow Technologies. Trillium has a long heritage of innovation spanning over 190 years. And the three pump brands being discussed today have a significant part of that history, with Flowway being founded in 1934, Turbomecanica in 1912, and Gabioneta in 1897, representing a wealth of capability and experience that enables Trillium to offer highly engineered solutions to our customers. And throughout this long history, Trillium has continually improved our products, added new products and services to better serve our customers. So this slide shows some of the different pump types as defined by the Hydraulic Institute, HI, and also by API standards. So in the top row, you can see the range of overhung designated OH1 through OH6 type pumps. In the middle row, you have between bearing pumps, BB1 through BB5. And then at the bottom row, you have vertically suspended pumps, VS1 through VS7. Trillium offers a full range of products to meet our customers' needs. And today we'll be focusing on the vertically suspended pumps shown in the bottom row. So here's a snapshot of the agenda for today's webinar. We'll be reviewing why one would use a vertical pump and what different types there are. We'll be going over vertical pumps used in different markets. So we'll be starting specifically with the water and mining markets, the oil and gas market, and also the power market. And as we go through these various areas, we'll see various applications, design features, and case studies for each. And at the end of the presentation, there will be a question and answer session. So all participants, please feel free to type your questions into the chat and we will address those at the end of the presentation. So starting with an overview of vertical pumps, why would you use a vertical pump? Well, the first consideration is NPSH, or net positive suction head, where suction pressures are insufficient to operate a horizontal unit. Often placing a vertical unit in a sump or a barrel is the only option. In these applications with limited NPSH available, pump cavitation is a true concern. The first stage of a vertical pump can actually be submerged as much as required, either in a sump or a barrel, to achieve the NPSH required to prevent pump cavitation. Another aspect would be cost. Often it's going to be lower cost to have a vertical booster pump to increase suction pressure to another horizontal unit versus increasing the pressure in the upstream system. And then also a vertical pump may be a less costly option compared to other pump types in various applications. Another consideration would be footprint. Being in a vertical orientation, a very large pump with many stages can fit within a relatively small footprint compared to other pump types. So why wouldn't you select a vertical pump? Well, there's definitely some very high pressure applications out there where a horizontal pump would better suit the needs of that application. And there also might be some foundation restrictions. Often it's not possible or practical to construct a large sump or sink a large barrel into the ground, depending on those site conditions. So as you can see on this slide, there are many different types of vertical pumps, and each can be uniquely configured to meet the needs of each application and customer requirement. There's no one type that's always correct, and Trillium has the ability to select and optimize each different pump type for any given application as required by a specification or the customer. And so the next slides, we'll discuss some of these examples in a variety of markets and applications. So we'll start with the water and mining markets. So this slide details a few common water applications and pump types used. The HI API designations are shown next to the respective pictures. So if we start on the left-hand side, this shows a VS1 pump type used in an open suction into a sump or a fluid reservoir, such as a lake or a river, and typically has an above-grade discharge nozzle as shown in these two images. And then in the middle, we have a VS0 designated pump or a submersible pump, where the motor is actually below the hydraulics, below the pump, and submerged in the fluid. This would be commonly used in deep well applications. And then the right two images show a VS6, or what we sometimes call a can or a barrel pump, where the pump is within a barrel. There's a suction flange and a discharge flange, so that the fluid is always fully contained within the piping system and the pump. And this would be a very common booster pump application and configuration. So typical water market applications shown here would include finished water pumps, high lift and low lift service pumps, booster pumps, well pumps, and raw water intake pumps. Additionally, reverse osmosis pumps, to name a few. Trillium actually provides many pumps for drinking water applications as required by customers and municipalities. And in these cases, we have an NSF 61 certified product line for drinking water applications, certified through UL. And these are constructed with materials with no lead or low lead. Typically, the materials have to have less than 0.25% lead by weight. And these products and pumps undergo third-party leach testing to ensure that no harmful chemicals or materials leach out of the pump product and into the drinking water that would then contaminate it. These third-party certifications typically include annual part sampling audits and quarterly factory audits to ensure compliance. And these are very similar to other requirements and regulations around the world related to equipment in contact with drinking water, including those in Europe and other parts of the world. And as an example, the image on the lower right-hand corner, you can see our NSF 61 certified pumps would come with a nameplate showing this third-party compliance. So jumping into mining applications, in general, mining applications require a large amount of water to operate and lots of pumps required at the process. Some of the applications would include water supply, treatment, and dewatering. This could be from lakes, rivers, or the ocean. Typically, there'll be booster pumps. There'll also be open pit or underground dewatering pumps. There will also be lots of process pumps. So this would include raffinate leach pumps, PLS pumps, a variety of reverse osmosis type pumps, and then also tailings pumps. And so on the images on the right, you can see a couple examples of a sump mounted and a barge mounted tailings pump that take the tailings water and pump it back up to the mine. So here we have a slide with a few major components of a vertical pump. Starting from top to bottom, at the very top is the driver. This is typically an electric motor, but can also be a right angle gear drive paired with a diesel engine or steam turbine, as is required. There's two main types of electric motors typically used, either a hollow shaft or a solid shaft vertical motor. And Trillium routinely provides motors from many different manufacturers including GE, Nidec, WEG, TECO, Baldor, Siemens, to name a few, really just depending on the customer requirements and the project requirements. The next component down is the discharge head assembly. This is where the shaft seal is and where the fluid exits the pump, and this is where the driver mounts. Below the discharge head, you have the column assembly. This can be configured to any length required by the project. We typically do lengths anywhere from 5 feet or 1 to 2 meters up to hundreds of feet or over 100 meters long. And this can also be configured in a threaded connection or a flanged connection. Typically threaded is a little bit less costly, but a little bit more difficult to maintain. And then at the bottom, you have the bowl assembly, which contains the hydraulic pumping components, including the impellers, bowls or diffusers, bearings, and shafting. And all of these major pump components have precision machine registers to ensure proper shaft alignment and operation when assembled. So there's two main types of discharge heads. The left image shows an example of a cast discharge head, and then the right example is a fabricated discharge head. So cast discharge heads tend to have more standardized dimensions. They're typically for lower pressure applications and are also a lower cost option. The fabricated discharge head can be fully customized to the dimensions required by the customer. For example, the nozzle location that's needed on the project, and can also be designed to handle high pressures and a variety of different packing or mechanical seal configurations. So pump testing. Trillium offers a full range of pump performance testing to meet customer requirements, and does this in accordance to HI and API test standards. This includes performance testing, mechanical run testing, MPSH testing, noise and vibration testing, could include hydro testing, and we can accommodate either on-site or remote witness testing as well. And so this table is taken from HI 14.6 and shows some of the different test tolerances and test grades that can be specified. So note the differences in flow, head, power, and efficiency tolerances as you move through the different grades. Grade 1U is a very common test grade for water projects in the US, whereas we see more 1B tolerances in Europe and other parts of the world. You want to be careful when you're specifying tolerances and looking at curves to make sure that you're comparing apples to apples when you look at the various test tolerances as well. Many applications may require different types of non-destructive examination testing, NDE, as required by the specification or project. So this can include dye penetrant testing, ultrasonic testing, X-ray, potentially mag particle testing to help ensure a quality pump product. So high efficiency pump designs. Why is this important? Well, high efficiency is important in most markets and applications. High pump efficiency reduces energy consumption and therefore reduces operating costs. Typically, energy costs make up the majority of the total ownership cost of a pump, and so this is a very important aspect. Trillium utilizes many different designs and techniques to offer world-class efficiency levels to our customers. And so here's a few examples of that. So starting with high efficiency hydraulic designs optimized using CFD analysis shown in the upper right-hand corner. We use high quality castings and tolerances on hydraulic components, especially on surface finish, which helps to optimize pump efficiency. We also use a variety of hydraulic coatings, polishing, and sometimes extrude honing, which can increase pump efficiency from about 1 to 3%, depending on the size and hydraulic design. And the lower right-hand image shows an example of a fusion bonded epoxy coating on a diffuser bowl. We also use tapered transition pieces in pumps and mitered or smooth radius elbows to help reduce hydraulic losses. So anytime you're able to avoid a sudden expansion or a sudden contraction or turn the fluid more smoothly through an elbow, you'll be optimizing the efficiency of that pump or system. Also, as previously mentioned, be sure to note the test grade, especially on efficiency that's being guaranteed. It can make a big difference if you're comparing two curves and one has a tolerance of -0 and another has a tolerance of -3 or -5%. So keep that in mind. So here's a mining pump case study of a flow-wave vertical turbine pump. In this case, it's a 650 horsepower VS1 pump made exclusively out of titanium. This is for a large copper mine in South America and shows just one example of a highly engineered solution provided by Trillium. In this case, the site was pumping a new leaching acid with a pH less than 1 to increase mineral yields from the mined ore. And due to the extremely corrosive nature of this fluid, all the major components had to be made of titanium. And it was actually a very specific grade of titanium that had, the customer had done a lot of lab testing and research to determine that it would hold up in this extremely corrosive environment. Another interesting aspect of this material was that although titanium is fairly strong and light, it's also about 2 times more flexible than steel. That is, the modulus of elasticity is about half that of steel. So to ensure low vibration of these units, these unique material properties had to be accounted for in the dynamic analysis of the pump structure using finite element analysis, or FEA, techniques. So now I'll turn it over to Luca to go through oil and gas.
Thank you, Dan. So after seeing the main application that Trillium can provide for the water and mining market, now let's switch to another market that is the oil and gas, the vertical pumps for the oil and gas market. This is the market for which the American Petroleum Institute standards were developed for. This is a standard that prescribes strict design rules in order to guarantee a high degree of reliability that is extremely important in plants where a malfunction of a pump might determine a loss in terms of time of production and a high cost of stop. So what strikes our attention in here, let's say, on the contrary of the water and mining pumps, where many complexity were found in the wide range of application in terms of installation, of different installation problems. Here we see a wide range of services in terms of liquid flowing through the pump, of operating conditions in terms of pressures, from very low to extremely high pressures, and temperatures, from very low temperatures, quasi cryogenic temperatures, as we will see, up to very high temperatures. And again, we have examples for that. On the right hand side, we see the three type of pumps that Trillium has specifically designed for the oil and gas market. These are the pumps inherited from the Gabioneta portfolio. Actually, there are pumps from the Flowway portfolio and the Thermomeccanica portfolio that are also suitable for the oil and gas market. So let's go on and see a little bit more in detail how these pumps are made inside. So let's see some cross section of this pump. As we can see, we have mentioned VS1 and VS6 together. They are basically the same type of pumps. The internal, the core of the pump, let's say the pump casing, the pump balls are the same, and the internal construction is the same. So they are single or multi-stage diffuser type pumps with the fluid flowing through the column and then out from the discharge head. The difference between VS1 and VS6 is typically the presence of the barrel, of course, as we can see from this image, and the application. The VS1 are typically installed over vessels or wet pits or sumps, and the fluid is coming from the bottom. While in case of VS6, we have a suction region, so the pump is flowing through the suction nozzle, as we see, down through the barrel, and then it is exactly the same as the VS1. So through the column is full of liquid, is in pressure, and then leaves from the discharge nozzle. VS2 and VS7 pumps are basically the same concept. So they are VS2 without barrel, VS7 with barrel with can, but the first stage is double volute, and also the double suction, as we can see from this image. Instead, VS4 pumps are specifically designed for other type of application. They're sometimes interchangeable with VS1 as they are typically installed in vessels or pits, but the discharge is through a separate line. It's not through the central column. So the central column is actually empty. This allows easier design of the upper part of the pump. There is no discharge head. There is actually just a discharge curve, and mechanical seal can be of a simpler design because it doesn't see normally any liquid, and in any case, it is not pressurized. So let's go on and put these 3 pump models into a coverage and see the main boundaries of the operating conditions. The VBN, this is the commercial name, but they are basically the VS1 and VSC and VS6 pumps, range from very low flows to average flows, but they can arrive to extremely high pressures. They have the highest pressure that we have in this range, up to 2,000 meters with 14 stages typically. That is about 6,500 feet. And again, pressure can go in this case from quasi-cryogenic temperatures. Now I state minus 100 centigrade degrees, so minus 150 Fahrenheit, but actually as a design metal temperature that they can be even lower. Let's go on with the VS2. It is typically, as I said, the same concept, but for higher flows. So they are double suction, and they are they can comply with low MPSH, even in case of higher flows up to a few thousand of cubic meters per hour, so more than 10,000 US GPM. And at the end, we have the VS4 that are only 1-stage pumps. The first stage is similar to the one of an OH2 pump, but the characteristic is that, and the flows are from very low to average flow. Actually, we arrive to a few thousand cubic meters per hour average heads. But what is interesting, and we will see in some application, we have an application for VS4 pump at extremely high temperature, up to 600 degrees. That is 1100 Fahrenheit, more or less, give or take. And so let's go on and see the common feature and the common option that we can install on basically all the vertical suspended pumps for the oil and gas market. The upper structure, so apart from the discharge head, the upper structure of the pump is very similar between the three, among the three cases. And this option of having or not having the rigid coupling is available on all three models. This can be useful to help the customer maintain mechanical seal without removing the bearing housing on top. So API require that mechanical seal can be maintained without removing the motor, but not without removing the bearing housing. So if the customer wants the rigid coupling, they can remove the coupling and maintain the mechanical seal. Otherwise, they have a saving in terms of height of the emergent heart of the pump. So it is just up to customer choice. Again, for easy maintenance operation, all the pumps are required to have replaceable intermediate bushings. What is interesting is the variety of the materials that that ensure the compatibility with all kinds of fluids, from the dirtier one, the one that can cause higher wear levels. In this case, we can also employ non-metallic solution, polymeric solution like PEEK, like a reinforced PEEK that can be suitable for these needs. And for low galling, and for application where low galling in case of contact is required. And then we also have all the pumps running run through FEA analysis, finite element analysis. So each and every pump structure is calculated, is computer calculated to be sure that we identify all vibrational modes of the structure and avoid them. We can intervene intervene if we find the resonances for the. Actually, we have a design specifically tailored for each application. So we have a way to intervene on the design in order to always avoid the resonances that might occur by calculation. Let's go more in detail, looking at the features of the VS4 pumps. So all bushings for the VS4 pumps, since the column is empty, need to be independently flushed by a separate line that, if the fluid is clean, can be spilled from the pump casing. So as we see in this picture, if the fluid is dirty, you will see arrows running downwards, because it is an external utility that provides the flushing fluid. What is interesting, and it is a particularity of our construction, is this line that is not separate from the column, but it is integrated, welded to the column, and this allows a much more robust design, especially in case we need to, especially for transportation, installation, and other action that have to be done on the pump. Customer might have fibrous or waxy fluids or solids inside the pumped medium. In this case, we can provide an open impeller, or even in case of fragile solids into the fluid that can be crushed, like Coke or similar, we can provide a solution, a Coke crusher solution, like is more common in horizontal overhang pump. Let's say it is pretty much the same, but it can be applied also on vertical pump. Now let's go on and see three special applications. The first two are for VS4 pumps. This one is an application that has been widely used in our history. It is the molten sulfur pumps. Molten sulfur has the characteristic of being pumped well only within a very narrow range of temperatures. So between 130 to 140, 45, maximum 50 centigrade degrees, so 200, 230 Fahrenheit. And so it is extremely important to have a constance of temperature. And this is why all these pumps are jacketed. Here we provide a full encapsulated design into a jacket can, let's say, that includes all the part of the pump, so no part is exposed to the exterior, let's say, to the external. But and what is interesting, here we see the description and the points indicating the features. But at the same time, given the very compact design of this VS4 pump, we can keep the dimension very contained in width. Again, as we have seen before, the separate lines, and typically for this pump, the nitrogen flushing with a dry soft packing seal is normally the sealing selection of choice. Here we see another application that from the construction point of view might be similar, but the application is totally different, because it is the application for molten salt pump. Molten salts are used typically for thermal energy transfer. It is used, and it requires to operate at extremely high temperature, from 400 to 600 centigrade degrees, so up to, as I said before, 1100 Fahrenheit degrees. And this implies some choices in the design of this pump. So the external barrel, the jacket, is no more required because it is the fluid is less sensible to changes in temperature. But in order to operate at such a high temperatures, we need to select properly the materials of both the column, the discharge head, and the discharge column, and the ceilings and any other component at the interior of the pump. Again, a seal, a soft packing dry seal with nitrogen is normally used, but it is important also to properly design the discharge pipe in order to allow the differences in length that may occur due to local differences in temperature between the column and the discharge pipe that is full with liquid. Actually, we see below some applications after 2017, we have done probably more than before 2017. So there are more that are not yet installed, but they are under construction. It is pretty much used in this. It is more and more popular, especially for solar plants where we have a lot of energy to be transferred, or when we want to heat up another medium without using devices like a direct heater to heat up the medium, because it is not applicable, or you need to transfer energy just by conduction because it is required. So here we quickly see some construction feature of this solution. On the right-hand side, the below part, so around the soft packing seal. Below we have the hot part. So we have an additional fan and a hot fluid barrier that are needed to isolate the hot part from the part above that must stay at lower temperatures. The stainless steel rigid coupling is required. It is not an option here because it is another feature that allows this separation between the two temperatures. And on the right-hand side, we see what is the typical design that we use for bearing housing. There is a separate chamber that is normally not required for other application. In this case, we have a separate chamber, a cooling chamber, typically cooled with water or other mediums, typically with water. And the performance of this cooling chamber is calculated through CFD thermal analysis. The last application we see is a particular application that has its own interest in itself, because it is an application that was at quite a high temperature. It was for crude, so it was insulated and with a lot of instrumentation. But what it is more interesting is how Trillium could provide a solution that in this case, fit the customer needs and anticipated actually the customer needs, because the customer in this case had a previously existing booster pump, that is this one, plus a main pump providing the total, the most of the head. But they had to increase the head of this train. So they asked to change the number of stages of the booster pump and to provide more head just by changing the booster pump. Now, this was not possible because it would have implied to increase the motor weight, and it was not possible for installation. Since the main pump was a Trillium pump as well, a Gabbioneta previously installed pump as well, we could change the design of the impellers. We could modify the internal design of that pump, and so the increase in head was divided between the booster pump and the main pump, providing the customer the solution he needed. Okay, now we can go on to the next section for the power markets vertical pumps. Okay. Andrea.
Thank you, Luca. Let's go through the power generation market for vertically suspended pumps. If we go to the next slide, in this table we can see to the left the main power process, and to the right the typical pump supplied, classified all according to API standard. For cooling water, mainly we found WES1 and WES2 pumps apply. Instead, for condensate extraction service, mainly WES6 and WES7 pumps apply. Once again, WES1 and WES2 pumps are vertically suspended, single casing with discharge through the columns. WES1 in particular is a single multi-stage diffuser pump with radial or mixed flow impellers. WES2 are volute pumps with double suction, radial impeller, and single or a multi-stage design. The operating range is shown in the picture at the center of this slide, in terms of flow rate in the horizontal axis and head in the vertical axis. A limit in this chart is shown for WES2 pumps in terms of capacity. This is not a technological limit, but so far imposed by market needs. Different customized solutions are available for power generation market and not only, and that give advantage for in some application. We can see in the next slide. Okay, WES pumps can be designed and supplied with a shaft protection sleeve, as shown in the central picture, and this sleeve protects the line shaft from dirty fluids. The advantage for customer is the possibility to pump non-filtered fluids, so avoiding big and very expensive strainers installed in the suction area. The guide bearings are in fact lubricated using a small amount of clean fluid, usually taken directly from the pump discharge, and filtered with a small basket strainer. We can have WES pumps can be designed as a pull-out. This solution, with this solution, the inner part, impeller, shaft, wear parts, and guide bearings is entirely removable from the outer part. The big advantage for clients is that after the installation at site, the outer part, that is the one with greatest weight, remains installed and only the inner part is moved. We will see an example also in the following stages. In some application, a gear reducer, as shown in this page, gives also some advantage. Thanks to the gear ratio, pump speed is not equal to the electric motor speed, and it's possible to install drivers with less pole numbers, so minor cost and less weight to be handled. A reducer gear is also installed as a rectangle gear for particular application between pumps and diesel engine or steam turbine. In the picture, a firefighting unit is shown, and diesel engine and gear are generally connected with a cardan shaft. This can give some benefits to civil works and alignment activities. WES1 pumps can be designed with adjustable impeller vanes, and this solution represents for customer a good and more economical alternative to speed variation. The device supplied and shown in the picture can change the impeller blade's angle when the pump is in operation and is rotating. The angle variation changes the pump performance. And then this solution applies for semi-open impellers and the spherical hub. For WES1 and WES2 pumps, the discharge flange is above the foundation ring as a standard. But in some application, when the discharge pipe must be below the foundation ring, we can integrate the delivery band in the upper column pipe, so below the sole plate. In this case, the customer can select the best routing for piping at site. Okay, when vertical suspended long shaft pumps are required, pumps with special devices called centralizer are designed. With this device, pump is just lowered inside a caisson or next to a vertical wall, and there is no need for customer to access the intake and fix the pump to the external structure. The number of positions of this device is always defined case by case to remove dynamic issues. For example, during pitch and roll in floating vessels. Okay, and WS6 and WS7 pumps are respectively a WS1 and a WS2 pumps, but installed inside the suction tank. So defined as a double casing according to API definition. The operating range is shown in the graph in terms of flow rate, horizontal axis, and head, vertical axis. Capacity is up to 20,000 cubic meters per hour and head up to 2,000 meters. Standard solution for WS6 and previous page. Okay, standard solution for WS6 and 7 is with suction flange above the foundation ring, so in the delivery band, as shown in both pictures of this slide. And a customized solution can be with the suction flange below the foundation ring, so directly in the suction tank. Okay, these are some references in power generation. We have listed 4 different power plants: nuclear, steam, combined cycle, and geothermal power plants. In all of them, we have installed cooling circulating water pumps, CCWP, condensate extraction pump, CEP, and horizontal boiler feed pumps, BFP, with different flow rate and heads mentioned. This is an example of a WS1 CCWP pump supplied in the power station of West Barton in the UK. 12,000 cubic meters per hour, 1 megawatt, and 48-inch the discharge flange. These pumps were installed in a water intake, a large basin that conveys water to the pumps. And for this type of installation, a CFD or a physical model test are made to identify hydraulic phenomena that can affect the performance of the pumps, like vortices or pressure, as mentioned in the Hydraulic Institute standard, and also shown in the 3 pictures to the right of this slide. In the left, a couple of pictures with a CFD result obtained for a water intake with multiple pumps in operation. 1 pump is standby and 1 of the 3 suction ducts closed. The CFD study of the water intake can be performed directly by Trillium R&D department, providing seamless optimization and time advantage for customer, avoiding third-party involvement. A WS7 CEP pump example for a geothermal plant in Italy. Here the impeller has been designed double suction to lower the MPSH required. So compared to a single suction impeller, the length was reduced, the speed was increased, and the supplied motor frame was smaller. Okay, let's go to the special application water industry. Again, to the left, the main processes for water and industry, and to the right, the typical supplied pumps, classified according to API. Here we can find mainly WS1, 2, 3, but also special design pumps like concrete volute pumps. That's an example of an impeller of a concrete volute pump supplied for the world's biggest pumping station in India for land reclamation and irrigation. Flow rate was 72,000 cubic meters per hour, so 370,000 GPM, 4 megawatt, and only 16 meters of head. As shown in the picture, the pump with the concrete volute and also concrete suction duct is completely integrated in the civil construction. And this is assured in particular for big sites, several advantages like reduction of installation cost, minimal and easy maintenance, and corrosion and erosion resistance, and increase of lifetime. Moreover, the pump is pull out with the advantage that we already explained. The guide bearings are 2/2 for easy maintenance and installation, and the seals can be removed without emptying the suction duct. Finally, hydraulic validation can be performed using CFD and or with a scale model test, completely homemade in Trillium. Last reference is for a VS1 pump for seawater supply in the desalination plant in Bahrain, 34,000 cubic meters per hour and 149,000 GPM, 4 megawatt. Customer required here a pull-out solution for easy maintenance. In the right picture, we can see the removable inner part composed by impeller, shaft, bearings, and the upper part of the delivery band, all lifted by the crane.
Okay, thank you, Andrea. So we have seen an overview of the portfolio and the solution that the Trillium can provide. Now let's do a quick recap. So why a customer would need a vertical suspended pump? The reasons have been highlighted by Daniel, but basically let's recap them. There are many applications where it is better or it is essential to have a vertical pump. A comparable horizontal pump is not suitable, basically due to space constraint and PSH available that is extremely low. That is too low for a horizontal pump. Due to the lack of horizontal pressure, of suction pressure, or simply for intermittent application where you just want to empty a vessel, it can be much more practical to have a vertical pump on the top of the vessel itself than having a separate pipe and then a horizontal pump. So there are many reasons, but sometimes, but in many cases, verticals are really the choice if you want to have to comply with some requirements. There are also a huge variety of design. The different design coming from the merge of the portfolio of different brands, different previous companies, allow to cover a wide range of application, a wide range, first of all, of operating condition in terms of flow. So from 1 cubic meter per hour up to 70 or 100,000 cubic meters per hour. That is 300,000 US GPM. And in general, what is interesting in this merger is that the Trillium companies merged their portfolio, but also their solutions to comply with all the customer requirements for different type of fluids, different temperatures, different operating conditions, different installation solutions. And so I think that we could give you a good overview and stress that our primary aim is this one, is to comply with any of the requirements that might come in these markets that we have presented. So let's go on and answer the questions that have arrived. Actually, we only have one question that is regarding the pump barges. I think that already Daniel has covered something regarding the barges.
Yeah, typically we'll work or refer barge type applications to third parties or work with third parties to do those designs and focus on the supply of the pump and the pump design in correlation with the barges. But we'd be happy to look at any specific projects that require barges. Yeah, and consider that in any case, if it is a barge that is related to a pump that can be in the portfolio of any of the Trillium brands, of any of the Trillium solution. As I said before, we have an integrated system that is becoming more and more integrated, so we can exploit in the solution that Daniel is presented also for pumps in other market, in other application, other pumps that are not
not among the one that was presented by Daniel. No, so this is the strength of this integration. So once a solution has been developed, it is ready to be used by all the solution in Trillium portfolio. And, now we have a second question. We have seen that some of your pumps, the performance curve goes down at low flow, and this is not meeting the API. Actually, it depends. I think that this is something that is it is related. I don't know exactly what curve you were mentioning. Typically, the pumps are designed not to be falling at shut off. But I think that this requirement is a requirement that is actually coming from the latest version of that is strict only in the latest version of the API. But anyway, all the pumps are actually designed for that. They're actually designed not to have a drop at shut off. So typically, when there is some figure like this, it can be due or interpolation of a very flat curve. This might occur. That might drop slightly at shut off. So I don't know exactly what picture are mentioning, but typically it is something that we want to avoid at all costs, and it is especially important in case of parallel applications. Okay. That's it. Do you have any others? Other questions? Otherwise, if there is no more question, of course you can post our questions to our contacts. We will be happy to reply. And I hope you enjoy and you find something interesting in this hour of explanation. Thank you all. Thank you all the audience. Thanks to my colleagues. Okay, I have seen another question. Yeah, what is acceptable level of vibration? It is a very difficult question to answer, not because there are no prescribed values, but the values change depending on the application, on the specification you are looking at, and if you are looking at the pump in test controlled condition or in plant condition, it might be different. So in plant condition, we prescribe for each type of pump a limit of vibration that is manufacturer standard, as an example. While in test, there are limits that in case of API pumps are prescribed by API or by other ISO specification or whatever. So there is no a single answer to this question.
Yeah, I mean, and there's also a few standards out there that can be referenced. So the Hydraulic Institute 964 has some vibration criteria for vertical pumps. And it actually has some levels for in the field and in the factory. And it varies by horsepower level of the pump. And then API would also have some limits on vibration as well. So those are some standards that can be referenced.
Exactly. When would you choose a gearbox over a variable frequency drive, except for reducing speed? Normally, it is not a choice that comes from ourselves. It is something that was already in our market. In the oil and gas market, at least, it was something that was already predefined, because the customer has the possibility to use a variable frequency driver. Actually, a gearbox in vertical pumps is not so common, as Daniel has shown.
Correct. I mean, yes, the question, when would you choose a gearbox? But, of course, again, with a gearbox, we have a fixed speed, but we are not linked to the speed of the motor. So the advantage to using a gearbox is that we can choose the speed we want for the pump and select a motor with a higher speed. So less poles number and less cost for the drive.
This consideration is valid. Oh, sorry.
Yeah, of course, with a VFD we can have we select a VFD when we need to cover a full range of performance. Not possible with a single speed design.
I would add that these considerations are much more common in horizontal pumps. It is more common to have an application where the customer wants to, let's say, do controlling of the pump operating condition by changing the speed. This is possible with a VFD. It is not possible with a gear. The gear is normally used to typically increase the speed over the synchronous frequency of the motor, or the maximum speed of the motor. There are different needs, and depending on the needs the customer have, one solution is chosen against the other, let's say. Overspeeding, it is something that normally it is okay. Noor is asking, what about overspeeding above the motor speed? It is pretty interesting. Actually, it is something that you want to avoid, because normally there are motors that are designed for overspeed. So typically motors are designed up to 3600 RPM. Not more than that. We can, so the motorist can accept a slight increase above that value, 3700 or something like that, but not much more because of typical construction. So there are motors for higher speed, for higher frequencies, but it is but they become a special motor. They are very expensive. So in that case, you probably, if you wanted to regulate regulate speed, but also run at a much higher speed, let's say 4,000, 5,000 or more, you can do this by coupling a gear and a variable frequency drive. Lowering, so the gear is the gear is increasing the speed, and the variable frequency drive is running through the speeds below the maximum speed of the motor.
Yeah, so I have seen a few applications where we use a VFD to overspeed a vertical pump. But since the pump horsepower goes up with the cube of the speed increase, you have to be, very aware of both the motor sizing and the VFD sizing to accommodate, maybe a 5 or 10% overspeed scenario.
For sure, we will share the presentation in form of a video. So it will be shared, I think probably on the YouTube Trillium channel or something like that. I'm not sure it is possible to share the material. It can be actually property of Trillium material, but for sure you can find all this information where we will share with the attendees the link to the video that will be published. So
thank you everybody for attending.
Thank you.
Thanks for attending. Thank you everybody, and thank you for the questions, and I hope you enjoyed.
Thanks.